In this lecture, we're going to continue with Chapter 24, covering sections 6 through 9 of electric potential. All right, so let's start with the potential due to a point charge. So a positively charged particle is going to produce a positive electric potential, and a negatively charged particle produces a negative electric potential. All right, so positive gets you a positive, negative gets you a negative. Consider a point P, a distance r from a fixed particle of positive charge Q. Imagine that we move a positive test charge Q naught from that point P to infinity. So we're taking this charge and we're moving it to infinity. Now the path chosen can be the simplest one, right? A line that extends radially from the fixed particle through P to infinity. So this is the line that we're following, just to keep things simple. All right, so we're going to use our equation for the electric potential, which is the final potential minus initial potential is equal to the opposite of the integral from r, which is the starting point, to infinity, which is in that direction. And then it's E times dr. Okay, so if we say that our final potential is equal to 0, which is at infinity, right, because that's where we're moving it to, and is equal to the initial potential, V naught, is equal to just big V, and that's going to be big V at r, right, just our distance r away from our particle. Then for the magnitude of the electric field at the site of the test charge, just going to be, so the electric field is just our electric field due to a point charge, which is 4 pi epsilon naught q over r squared. So if we plug that electric field into our potential equation, we get 0 minus v, right, because our final potential was 0, is equal to the opposite of q over 4 pi epsilon naught times the integral from r, which is our position away, all the way to infinity, 1 over r squared dr. And this is going to be our total electric potential. Okay, so just doing that integral, it's a simple one. We will just end up with q over 4 pi epsilon naught. And that is from, and then you just get 1 over r, of course, and that's from r to infinity, big R to infinity. Okay, go ahead and plugging in our two r's here. Well, if we plug in big R, that's obviously going to get us 1 over big R. If we plug in infinity, it's going to be 1 over infinity, which is going to go to 0. All right, so all we have left is the opposite of 1 over 4 pi epsilon naught, times q over big R. Okay. Now if we just switch big R back to little r, and we can do that because this r might not, this big R is not a set distance, so we can just change it to any distance away. So we'll just change that back to little r to keep our notation straight. All right, so V is equal to 1 over 4 pi epsilon naught q over little r. All right, so that's going to be our potential due to a point charge. Now let's look at this. Well, this is a linear relationship. So the further you get away, the electric potential is going to change in a linear fashion, not a squared fashion or an inverse squared like we have up for the electric field. So the equations are very similar, but the electric potential is only changing in a linear fashion. Okay. Now, the net potential at a point due to a group of point charges can now be found with the help of the superposition principle. And the superposition principle just lets us add all the contributions together from each charge. So first, the individual potential resulting from each charge is considered at a given point, and then we sum all the potentials together. All right, so if you have n number of charges, which is just however many charges we have, the number of charges, the net potential is going to be the sum of all of the potentials from, starting from 1 all the way to however many you have. All right, so this is simply 1 over 4 pi epsilon naught times our charges divided by the radius away. Now notice this isn't a vector, so the potential is not a vector, which means that the direction doesn't really matter. The only thing that matters is going to be the sign, so positive or negative. So the orientation of all of these charges in relationship to where we're trying to find the potential doesn't matter. Okay. So just let me, actually in the next slide I think we'll do an example. Yeah. So what is the electric potential at point P, located at the center of the square a point charge is shown? Now the distance is d, which is 1.3 meters. That's the distance between each of the charges, and the charges are listed. Okay, so the electric potential, V, at point P is the algebraic sum of all the electric potentials contributed by the 4 point charges. Again, where they are situated doesn't really matter. All that matters is the distance away from the charge, or from the point, excuse me. Okay, so again, because the electric potential is scalar, the orientations of the point charges do not matter. All right, so then let's go ahead and work this out. All right, so our electric potential is going to be the summation of I is equal to 1 to 4, because we have 4 different charges. And that's just going to be all the potentials added together. All right, so using our equation, we have 1 over 4 pi epsilon naught is equal to Q1 over R plus Q2 over R plus Q3 over R plus Q4 over R. Now, in this case, R is the same for all the charges. All right, so we're just keeping it as the same variable. Okay, so R is just D over square root of 2, and we did this by just making a triangle. You make this triangle here, and you have d squared plus d squared, and to take the square root of that, you see that this distance right here is just d over the square root of 2. Okay, and so if we just plug in our value for d, which is 1.3 meters, we get 0.919 meters. Okay. So since our denominator is all the same, we can just add all of our charges together. So if we add Q1 plus Q2 plus Q3 plus Q4, it's going to be 12 minus 24 plus 31 plus 17. And this is all times 10 to the negative 9 coulombs. Our total charge, Q, is 36 times 10 to the negative 9 coulombs. All right, so we take these two results and plug them into our equation for the electric potential, and you get, it's going to be K, so 1 K times everything else, so 8.99 times 10 to the negative 9 coulombs, times our charge, which is 36 times 10 to the negative 9 coulombs. And this is divided by 0.919 meters, which is our distance. So we get our electric potential is 350 volts. Okay. So close to any of the 3 positive charges, the potential has a very large positive value, and close to the single negative charge, the potential is going to have a very large negative value. So therefore, there must be points within the square that have the same intermediate potential as that of point P. And this picture here is showing you what the equipotential surface would look like. It's just going to look like that. You can find this out by, calculating at what points all of these would be. Okay. Put my head back here. All right, so let's do another example. So again, potential is not a vector, and let's drill that point in a little more. So in the figure, 12 electrons, each of charge negative e, are equally spaced and fixed around a circle of radius r. Relative to v is equal to 0 at infinity, what are the electric potential and electric fields at the center, which is point C, of the circle due to these electrons? So we have points evenly distributed around. What is the electric potential at the center? All right, so the electric potential V at C is the algebraic sum of all the electric potentials contributed by all the electrons. All right, so you're going to have this electric potential, etc., with actually negative charges, so they're going in the opposite direction. Oops. And we have to add all these up all the way around the circle. All right, so the electric field C at the is a vector quantity, and thus the orientation of the electrons is important. So if we're trying to find the electric field, we need to worry about where these charges are actually located. But if we're just trying to find a potential, the location doesn't matter. The orientation doesn't matter. So because the electrons all have the same negative charge E and are all the same distance r away from C, our equation just gives us this. So we just add all the charges together. They're all negative E. So you have 12 times negative E divided by r, which is our distance away. Now, because of symmetry of the arrangement, the electric field vector at C due to any given electron is canceled by the field vector due to the electron that is diametrically opposite. Thus, at C, E is equal to 0. So this contribution to the electric field is going to be canceled out by this contribution to the electric field. This one's going to be canceled by this one, and so on and so forth. So you end up with E is equal to 0 at C. Now, if the electrons are moved along the circle until they are non-uniformly spaced over a 120-degree arc, what then is the electric potential at C? Well, the potential is going to stay the same because the distance r of each charge stays the same. So you're going to end up with this equation again. But how does the electric, now how about the electric field? How does that change, if at all? Well, this is going to change because the orientation changes and the electric field is a vector. All right, so you're going to end up with an electric field that's probably overall somewhere in that direction, since they're all negative. Okay. So let's talk about the electric potential due to an electric dipole. All right, so at point P, the positive point charge at a distance r positive set up an electric potential V positive, and the negative point charge at a distance r negative sets up a negative potential. All right, so we have two charges. This is going to set up a positive potential. This is going to give us a negative potential. They're separated by a distance d apart. Our location O is right at the middle between them. And then we have an angle theta that goes towards our point. Now, the r from our positive charge is just going to be r positive. R from our negative charge is going to be r negative, just so we can keep track of which r we're talking about. So our net potential at P is going to be given by our equation. Right, so V is equal to the summation of I1 to 2, since we only have two charges, of our potentials, is equal to our positive potential plus our negative potential. And that's going to be equal to 1 over 4 pi epsilon naught. And that is going to be Q over our positive r plus negative q, because we have a negative charge, over our negative r. Oops. Okay. All right, so this can be simplified a bit if we multiply this first term by r minus over r minus, and then our second term by r plus over r plus. All right, so if we do that, we have q over r plus r minus times r minus, oops, and that's going to be plus negative qr plus over r plus r minus. And this gives us two terms with the same denominator, so we can add them easily together. Now, so since they have the same denominator, if we add them together, we can see that the q's are just going to cancel out. So all we end up with is r minus r plus divided by r plus r minus. Okay, so the potential is really just going to be the ratio of the distances away. Okay. All right, so naturally occurring dipoles are quite small. We've talked about dipoles before. We haven't really talked about how they occur, and in the next couple of slides we'll see maybe an instance that they could occur. So we are usually interested only in points that are relatively far from the dipole, right? Since the distance between the dipoles is so small, we're usually interested in distances that are pretty far from it. All right, such that the distance between them is much smaller than the r away, or the distance away from our point P. All right, we're D. Okay, so also, if we remember, our dipole, our electric dipole, is going to be P is equal to QD. So the dipole is just equal to QD. All right, so let's make a couple assumptions. Now, if we said that R minus minus R plus, which is our top term here, is relatively close to d cosine theta. And we can see that. I mean, just think if you had the point P all the way up here. Well, this minus this, right, these distances, or I should say, this distance minus this distance, would just be d, right? And if you had cosine of 0, which would be the angle between our two vectors, that's just going to be 1. All right, so that gives us just d. So that makes sense. Now, if you had a p all the way out over here, the distance, the difference in distance would be relatively small. So we wouldn't even have to worry about the distance, or the change in distance, I should say. So that would just be 0. Okay. All right, so we're going to make this first assumption, and then our second assumption is that, well, r minus times r plus is pretty close to just r squared, where r is the distance from the center all the way to our point. All right, so that simplifies it quite a bit. You take these two assumptions and you put it into our equation, and you end up with q over 4 pi epsilon naught times d over cosine theta, which is our first assumption, divided by r squared, which is our second assumption. Now, QD is just P, which is our dipole moment, so the potential due to a dipole is going to be 1 over 4 pi epsilon naught times the dipole moment cosine theta divided by r squared. Okay, so let's talk about some instances of where a dipole could occur. So this is going to be an induced dipole moment. And so an atom is showing the positively charged nucleus in green and the negatively charged electrons in gold. So this is our atom, and then in the center you have our positively charged nucleus. You have the negatively charged electrons around it in the cloud. If the atom is placed in an external electric field, right, some external field, the electrons or orbits are distorted so that the centers of positive and negative charge no longer coincide. So now you have this positive charge, and this is exaggerated, but it's pushed off towards the edge of the cloud, and now the negative charge is still located over here in the center of the cloud. All right, so you create this positive and negative charge, and that creates us a dipole moment. Okay, so let's do the potential of a continuous charge distribution, which is a line of charge. All right, so we have a thin, uniformly charged rod produces an electric potential V at point P. All right, so here is our charged rod. Here's our point P away from that charged rod. It's a distance of d away. All right, so an element can be treated as a particle. The potential at point P due to the element depends on the distance r, and we need to sum all the potentials due to all the elements from the left side d all the way to the right side e. All right, so if we just take this little differential element and we'll say, well, that can be described as a point charge, and we take the contributions from all these little differential elements to point P, that'll give us our total potential. All right, so if the lambda, which is the charge per unit length, then the charge on the length dx, which is our little differential element, is just going to be dq times lambda dx. Okay, and we can see that because we know that lambda is equal to charge over a unit of length. So our unit of length in this case is dx, which means this is dq. Okay. Okay, so, and then our radius r is just going to be, using the Pythagorean theorem from the triangle that we create here, we get x squared plus d squared to the 1/2. Okay, so let's go ahead and start writing this out. So so therefore, our differential potential is equal to 1 over 4 pi epsilon naught times dq over r, where we know dq is 1/2 4 pi epsilon naught. dq, oops, is just lambda dx, and this is divided by x squared plus d squared to the 1/2. Okay, so let's go ahead and take this onto the next page because we're going to need a lot more room. All right, so again, our dv element is equal to 1 over 4 pi epsilon naught times times lambda dx divided by x squared plus d squared to the 1/2. All right, so we want to find the total potential, so we need to take the integral. So our total potential V is going to be, the integral of dV. So it is the integral from 0 to L, because right, we're going from our 0 point here all the way to L in the x direction. All right, so those will be our bounds of integration. This is 1 over 4 pi epsilon naught lambda divided by x squared plus d squared to the 1/2. Okay, and this is going to be all multiplied by dx. All right, so this is then going to be equal to, if we pull all of our constants out, we have lambda over 4 pi epsilon naught times the integral from 0 to L of dx over x squared plus d squared to the 1/2. Okay. So then we realize that we have an ugly integral, this one right here. It's not an easy du situation, a little more complicated. So what we do is go to our integration table, and we find out that the solution to this integral is simply put our constants in, 4 pi epsilon naught. So it is the natural log of x plus x squared plus d squared to the 1/2. And then we have our limits of integration from 0 to L. All right, so next up we want to go ahead and put in these limits of integration. We do need to consider this 0 because when we put this 0 in here, you get get sort of the x's, but the d squared is still there. So d squared to the 1/2 is just going to be d. All right, so let's go ahead and put the limits in, and we get our constants out front. Whoops, let's try that again. Our constants out front times the natural log of L plus L squared plus d squared, and that's to the 1/2. 1/2 minus, whoops. Let's see, there should be another parentheses there, minus the natural log of d. Okay. Now, we have the natural log of something minus the natural log of something, which means it's the natural log of the first divided by the second. So this simplifies to lambda over 4 pi epsilon naught times the natural log of our first one, which is L plus L squared plus d squared to the 1/2 divided by d. Okay? All right, so this is our electric potential due to a line of charge. Okay, so we have one more topic to cover, the potential due to a continuous charge distribution, which is a charge disk. All right, so now we're not doing a line charge, now we're just going to do a charge disk. So in the figure, consider a differential element consisting of a flat ring of radius r prime. All right, so let's be pretty straight with our notation here. R prime is going to be our distance from the center to some ring. Now R prime is going to be a variable in this case. Even though it's a capital, we're using it as a variable. I kind of wish your book used a lowercase r prime or something just to keep it straight, but so r prime is going to be a variable. R without the prime is going to be the total distance from the center all the way to the edge of your disk. All right, so we need to find dq. Well, dq is just going to be our area charge density, which is given by sigma, times the circumference, right? Circumference of our circle, which is just 2 pi r prime, times dr prime. And that gives us this little differential area element here. All right. Okay, so the contribution of this ring, just this little orange ring here, to the electric potential at P, which is some distance z away, is going to be given by dV, right, which is our differential potential element, 1 over 4 pi epsilon naught dq over r. So we're just starting with the same equation we had before. We're going to plug in what we have for dq up here, and we get 1 over 4 pi epsilon naught times sigma 2 pi r prime dr prime divided by square root of z squared plus r prime squared. So this is r prime squared. Right, so it's this times this gets you r. All right, so the net potential at P can be found by adding, via integration, the contributions of all the rings. So if we start with rings very small, and we build our way all the way out, and we go ring after ring after ring after ring, we integrate all the way through the surface. We'll start from r0, or r prime 0 to r prime is equal to r. All right, so our total potential is then our integral of dV. Pulling out the constants, we have sigma over 2 epsilon naught. We have 2 epsilon naught on the bottom because this 2 pi here cancels out with this pi and 4 there. So you just get over 2 now. Okay, and then you have the integral from 0 to big R of r prime dr prime divided by the square root of z squared plus d squared. Oops, excuse me, not d squared. This is r prime squared. R prime squared. Okay. All right, so what's this equal to? Well, this is an integral that's actually a little more straightforward. You can say that u is equal to z squared plus r prime squared, which means du is simply going to be 2 r prime dr prime. All right, z is not the variable in this case. Our r prime is the variable, like I mentioned before. Okay, so now let's do just this integral quickly. Move my head out of the way. All right, so this integral is going to be, all right, so we're going to do a 1/2. We'll bring the 1/2 out because we have this 2 here in the du that we don't want to worry about. So I'll pull the 1/2 out. I'll get du over u to the 1/2. That is, of course, u to the 1/2 divided by 1/2 with some limits. I'm not going to worry about changing all the limits over because we're just going to flip everything back into our previous notation. So this 1/2 is going to cancel out with our 1/2 over here, so don't have to worry about that anymore. And you end up with sigma over 2 epsilon naught z squared plus r prime squared to the 1/2. I'm just plugging u back into the equation. And now our limits are from 0 to r in this case. Okay, so now this is relatively straightforward. You just plug in 0 and you plug in r for our limits, and we get our final answer of sigma over 2 epsilon naught times the square root of z squared plus big R squared, which is not a variable, minus z. All right, and that is equal to our electric potential due to a charged disk. All right, that's it for this lecture. Next time we'll cover the last couple sections of Chapter 24, and that'll be it for the chapter.